Recording is rolling. Today is Wednesday, September 21st. So you guys were about to do a Kahoot on Newton's laws of motion. So I have three Kahoots lined up, one for each of his laws of motion. Okay. You guys remember this packet you got about a week or so back? Okay. Has Newton's law spelled out on the back? Okay. So the first Kahoot we're going to do is on just the law of inertia, and I'll see how far we get today. Maybe we'll get this far, maybe we'll get this far. Okay, and then third, yeah. Eventually do all these with you guys. Okay. Okay, so you guys have the questions, you can follow along if you like. You guys remember the quizzes I give you guys to focus mostly on those questions, right? And I'll throw some other type questions too. Might be a graph, might be a fruit body diagram, might be a little calculations going on. Oh, tell you guys too, you guys remember this whole deal about you're supposed to get laptops from the school, like every single student's supposed to be assigned a laptop. Right, so faculty meeting this morning, and info I have on that is it's gonna be Friday, October 28th. We're gonna take that whole day, it's gonna be the laptop day. So probably won't be doing much content in any of your classes, including this one, because we're just gonna take the whole day. I don't know exactly how it's gonna pan out, but you're gonna get the laptops in your hands. There's supposed to be like this whole process. You're supposed to like watch certain videos and da, 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 da. So anyway, that's coming up about a month from now. Yeah. So coming down the line. Okay. Before I run the Kahoot with you guys, the other thing is, you guys remember this PowerPoint with three body diagrams? We're actually really close to the end, so I figure let's just go ahead and finish these off first with that. Okay. And this is the last one you guys saw yesterday. If there's a block on an incline, then there are three forces on it. It's weight down, the normal force up to the left, and if it's at rest, there's also a friction force holding in place, pointing up to the right. Okay. Right. And then I took you guys through this process of, well, if you did any kind of analysis on this, now this might be a little bit beyond the scope of this class, but stretch your guys' imagination a little bit, probably helps you see. Right? If you did any kind of analysis, you have to say, well, the motion of the block is constrained along the surface. So we're going to introduce a Cartesian system that is also aligned to the surface. You guys see like a little dash line there, a little dash line there. Right. Now, two of those forces are already aligned to that system. Right? The normal force, because normal is perpendicular to the surface, so and by definition it will be. Right. And then the friction force is always perpendicular to the normal force or parallel to the surface. So that's also aligned. But the weight you have to break into components. So I did here with these dashed purple component vectors, right? And then you can make sense of that. Now, do you guys see how the mg cosine theta exactly balances out the normal force? And see how the sine component of the weight, mg sine theta, exactly balances out the friction force? That could put it in equilibrium, for example, at rest. There you go. And then next slide. What if the block is sliding down at constant speed? Hey guys, constant speed, or constant velocity, I should say, is that, well, what's the acceleration for constant velocity? Zero, right? If there's zero acceleration, what's the net force? Also zero. So would that block also be in equilibrium at constant velocity? Yes, it would be. And what that means is that the free body diagram looks exactly the same as the last slide, right? Maybe technically the difference would be this friction would be kinetic friction instead of static friction, right? Which might have a slight different angle for the given materials, but otherwise it pretty well looks the same, right? The force is still balanced, right? In fact, if all you had was the free body diagram and you had no other context, you wouldn't even know if that block was at rest or sliding down at constant velocity. It could be either one because those free body diagrams look pretty well identical, right? Next slide. Hey, what if this block is sliding the other way? Right now, this one actually will be different. The free body diagram is going to be different. Okay. One thing that's going to change. What's the one thing that's going to change? Let's see. Is its weight still the same? Yeah, still has the same gravity force. In fact, those components are still going to break down the same too. How about the normal force? Is that still the same? Normal force? Yeah, so that's not going to change. Ooh, what about the friction force? Something about the friction. What changes about the friction force? Okay. Let's get started out here. So the weight's the same. The components of the weight, of course, are the same. The normal forces are the same. Okay. Now, remember before when the block was either at rest or sliding down the incline, the friction force was pointing kind of up and to the right for both those cases, right? But if the block is kind of sliding up the incline, which direction do you think friction points? Is friction always going to oppose the motion? It sure will. Yeah, friction will oppose the motion. You guys see that's going to be different. So now, so big picture point of view here. Is that block in equilibrium? It no longer is because there is a net force. Let's see what the net force is. Okay. well, I replaced the weight in terms of those two purple dash components. So we're gonna, yeah. So ignore the weight vector straight down because we can just look in terms of those two dash components. Okay. It looks like the mg cosine theta and the normal force still cancel out. So those balance, don't worry about those. Okay. But there's two forces that combine to make the net force. The mg sine theta, right, the sine component of the weight, and also the friction force. Those add together. Looks like they're both conspiring to slow down that block in a hurry, right? Because the block is moving up to the right, but there's a net force the other way. Okay. All right, tomorrow I'm gonna have you guys do this right here. You guys remember yesterday I demoed this for you guys, broke out that pulley, some strings, some weights. Right? You guys gonna see what's the relationship of say if you change out these masses, how does that affect the acceleration of the system? There's going to be a process for that. You guys are going to figure that out. Right? But today, since I got this slide up, let's say, what's going on with the forces specifically? Because that's a different way to approach this. Tomorrow, you guys are going to approach it empirically. Today, we're looking at it from a forces point of view. Do you guys think that each of those weights I should say this, each of those masses has a weight pulling down? Yeah. Right. Now it looks like I have the big one on the left and the small one on the right. So weight would be proportional to mass, right? It's 3 times the mass, be 3 times the weight. Right? That's kind of what those force vectors look like. So we got that. Each of those masses has a weight. Right? Now, actually, if you just sort of stop right there, those are the external forces that are going to drive the system. And this is one way to approach this problem. Tomorrow, you guys will approach it empirically, which will be a little bit different thought process. Okay? But do you guys think that those are kind of in tug of war, right? And that the difference in those weights is going to be the net force driving those blocks to accelerate. In this case, counterclockwise, right? M2 is going to accelerate down and one's going to accelerate up. Okay. So this is approaching it from a macro point of view, like a big picture point of view. Now, if you want to get more granular and focus on an individual block at a time, like let's say we focus on M2, right? There is another force on M2. What is the other force also on M2?
Other than gravity?
Yeah, right. Other than its own gravitational weight. Is there something pulling this block up, sort of? Yeah, the string, right? This tension. Right. And same story for M1. Maybe I should take this as an example, because there's definitely a tension pulling up this one, right? So it's driving it upward. Right. There we go. I have T for the tension force. I've tried to switch over the last couple of years to do an F sub T for tension force to distinguish it from time period. But here, capital T could be tension, right? Hey, do you guys notice if there's one string and it's winding around a frictionless pulley, right? Massless frictionless pulley, approximately, right? How many tensions can there be in one string? It's one tension, right? If everybody's playing tug of war, there's only one tension in that string, right? That's kind of what's going on here. Do you guys see that the upward tension is the same magnitude on both of those, right? But the net force is a different direction for each block. For M1, see the net force would be upward. The tension beats the weight of M1. But for M2, you guys see that the weight of M2 is going to beat the tension. So M2 is accelerating down and M1 is accelerating up. You see that? Right. All right. So that's more like a micro point of view, right? See if I scroll back a little bit. There's your macro point of view, like system point of view, this driving system to move, okay? Which could solve the whole thing if you want to know what's the acceleration of the system. Okay? But if you want to dive and get more deeper, if you want to ask the question, like for example, what is the tension in the string? Then there you go. You do that. Now that tension is internal to the system, so it's just holding everything together. So it's not actually an external force, meaning it's not driving an overall acceleration of the system from a system's point of view, but it's just holding the whole system together. Okay? Now, if you want to do total overkill, you say, well, what about like holding the pulley in place up here, which could be part of the picture too. So it's got its own free body diagram. So if it has the tension pulling down on each one, and you're probably holding up with probably double that tension force. So something like that, right? Okay. What else we got? Modified Atwood. So what if you, okay, that looks kind of like the Atwood, just one block moves horizontally. Right? Do you guys think you could take make this surface like an air hockey table and maybe get rid of all the friction if you like, right? Or maybe you could slip a Hot Wheels car under there and have pretty well the same effect, right? Add about 30 grams and get rid of the friction for the most part, right? Wonder what this looks like. So each of those blocks has a weight, but notice the one that's hanging is actually providing an external force that's going to drive it to move, because the one on the surface, M2, well, that's going to be balanced out by the normal force. You guys see zero net force on M2, right? Except that's not exactly true because I still have to put in the tension. There it is. There's the tension, right? Now the tension is going to drive M2 to accelerate to the right. That would be the net force on M2 at this point, right? I should say there's zero net vertical force on M2, but there's the net force is the tension. Okay. And see how for M1, the weight will always be more than the tension, so there's a net force downward. All right. So there you go. There's some food for thought there. Close out that one. All right, you guys ready for Kahoot? All right, here we go. All right, so you guys got your cell phones up. You got a moment there. Yeah, pause this video while you guys are hopping on here. All right, recording is resumed. Oh, look at all those players. All right, all right. All right, you guys ready to answer some questions about Newton's first law of motion? You guys are following along? Here we go. Galileo found that a ball rolling down one inclined plane would roll how far up another inclined plane? Ooh, got one winner to its original height. Okay, so let me switch over here and draw this out for you guys. Let's see exactly what's going on with this one. Okay. Actually, I should tell you guys too, the text I pulled these problems from, there's actually a Paul Hewitt's text. You guys remember Paul Hewitt? Okay. Yeah, I don't know. I think that's more of a conservation of energy type question, but I guess it tangentially works here, right? So remember, here, I'll just draw this out for you guys, and then we'll for Newton's first law of motion. You guys remember what we're going with here? Okay. So Galileo was one of these first scientist types who actually collected empirical data, didn't just sit down in an armchair and think really hard how the world worked. He actually got and tried things out. Right? Usually I reference his Leaning Tower of Pisa experiment, right? Dropped a ball off Leaning Tower of Pisa, actually dropped different masses. They all fell at the same rate. So this experiment we did, you took a ball, you put it right here, okay? And say it was like some height above the lowest point. Well, it's like H, right? And he's like, I wonder how far it's going to roll up the other side. Okay. And the theoretical limit and what he found, or at least what he reported finding, was that the ball did in fact go right up to the other side. Okay. That would be exactly true if there was no frictional losses. And so suppose this was like in a vacuum and there was like magnets, so it was like levitating. They could just do this all day, every day for like thousands of years. Okay, there it is. So roll from that height to the exact same height on the other side. Okay. Actually, while I got the screen flipped over, let's take a peek at Newton's laws of motion. So first law of motion, remember this is the law of inertia. So most of the questions are pretty closely aligned to this one. An object at rest will remain at rest. An object in motion will maintain its velocity. And by that, you guys know what velocity is. It's two things. It's speed and direction of motion. Okay? Unless there's an outside force acting on that object. Right? If there's no outside force, if there's no external force, then an object will either remain at rest or just keep doing what it's doing. All right, let's see who got the Galileo question. We got Harry with some points on the board. All right. The law of inertia states that an object, what, unless an outside force acts on it? Yeah, it's okay. All right. So you guys just saw I read that off to you, right? Right. And all those statements are true. Right? An object at rest will remain at rest. Bing, that's true. An object in motion will continue moving at the same velocity. Bing, that's true. An object in motion will continue moving in a straight line, which is also embedded in the fact that it has the same velocity, right? Keep moving in a straight line. So bing, that's true too. Yeah, those are all true statements. Those are all parts of the first law of motion, law of inertia. All right, Nikki and Olivia, picking up some points. The law of inertia applies to what? Oh, yeah. Sorry, I don't have an iPhone. Yeah. There you go. It applies to everything, right? The first law, actually, all these laws of motion apply to everything, don't they? Right? Yeah, we'll sort of amend that when we get to relativity, but there we go. All right, Nikki taking the top spot. We got Alex, Harry, Leah, and Olivia. I'm not top 5. After a cannonball is fired into frictionless space, the amount of force required to keep it going equals. All right. Okay. Yeah, 0 newtons. No force is required. Remember the classic example I told you guys the other day was Voyager spacecraft, right? Voyager spacecraft has been going since 1970s. It's at the edge of our solar system now. And it's just keep on going. Is it ever gonna like run out of gas and just like come to a stop? No, because to come to a stop, that would be hard. That would require a huge force for it to stop. It's just gonna keep going because of Newton's first law of motion. Now switch out Voyager 1 with the cannonball, and you got this premise right here. It's the same idea, right? You guys good? If you guys have questions on any of these, then let me know. Right. Ooh, got Nikki on fire, Olivia up to 2nd, Harry, Alex, and Leah round out top 5. If the force of gravity suddenly stopped acting on the planets.
It's actually red.
Yeah, the yellow one, they would move in straight lines tangent to their orbits. Okay. So we'll talk about orbits a few weeks from now. But remember, if something's in orbit, it's constantly changing its direction, which means there must be a force on it. Otherwise, that would break Newton's first law of motion. Right? That force, you could call this centripetal force. In this case, it would be provided by gravity. So the gravity force would be acting as the centripetal force. And if you stop the force, if you just cut that force off, then now we're back to Newton's first law of motion. Everything just wants to move in straight lines, which would in fact be tangent to its path. Let me switch over in case you're need to say again, because I gave you guys a picture, but you could only see that picture while the question was up. Okay, so here we go. So we got the sun. Okay, we got a planet. Here's its orbit. It's going around. Okay, so there's a gravity force that's acting as a centripetal force that's holding it in orbit. Okay, but then if you suddenly cut the gravity force off, here comes the planet, and you cut off right here. Bam! It's just going to continue in a straight line this way. Okay, break out the ruler, make a straight line, right? Tangent to its orbit. Okay. You know what? This is the exact same scenario. What if you had a ball on a string? Suppose to put a string right here. This is your hand. You have a string. You wheel it around. You cut the string. Is that ball also going to move tangent to its path? Yes, it will. Okay. Now, it feels like it wants to fly straight away. That's what it feels like from your hand. But really, that tension is providing that tension force is acting as a centripetal force holding the ball in orbit. And then if you cut that string, yeah, Newton's first law of motion takes over and moves tangent to its path. Okay, everything just wants to keep moving, same speed, same direction as it's already going. So same velocity. All right. Nikki, hold on, top spot. A sheet of paper can be withdrawn from under a container of milk without toppling it if the paper is jerked quickly. Because why? Yeah, milk carton has inertia. Right? So mass could be a measure of inertia. If something has 3 times mass has 3 times the inertia. If it's floating out in space, right, then the amount of mass represents the amount of inertia. Hey, suppose you guys were in International Space Station. Could you guys imagine you're floating around with all your astronaut friends, right? And you're throwing stuff at each other. So would you rather, what would you rather have headed straight at your face? A tennis ball or a bowling ball? Tennis ball, right? wait, even though neither of them have any weight, because you're floating around, right? But they both have a lot of mass, both have a lot of inertia. But that tennis ball is kind of easy to stop even in space, but the bowling ball, it's gonna like plow through. Yeah, looks like this, right? Here, show you guys this in action right here.
And what do we have down here again? We have some plates, no staples, no Velcro, the tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
Ooh, look at there. All right. So if one of those objects was a milk carton, that would be exactly that right there. There you go. Olivia, to your top spot. An object has twice as much mass as another object. That means it also has twice as much inertia. Yeah. So twice the mass, twice the inertia. Okay. Is there any question about the other ones? Okay. So remember that anything could be moving at any velocity. So that one's kind of out. Okay. So somebody has chose all the above. Okay. Guys, gravitational acceleration. You guys remember this whole deal about you guys did this with the car and ramp lab. You guys remember changing out the mass of the car and they all accelerated the exact same down the incline, right? So this is the same for all objects at the surface of some planet, right? Yeah. More mass, more inertia. Compared to its weight on Earth, a 10-kilogram object on the moon will weigh what? Yeah, less, right? Well, way less, has less gravity force on it, right? But does it have the same mass on the moon? Yeah, 1 kilogram on the Earth is still 1 kilogram on the moon, okay? But it weighs about 10 newtons on Earth, and it only weighs about 1.6 newtons on the moon. Yeah, so you guys are right. Same mass, less weight on the moon. Compared to its mass on Earth, the mass on the moon is what? There you go, the same. Yeah, same mass. Same mass. Right. Is there a question about that? Okay. So same mass, same inertia. Okay. All right, we've got Luca in fifth, Nikki, Harry on fire, Alex and Olivia, top spot. The mass of a sheep that weighs 110 newtons. How many kilograms is that? All right. You guys are pretty good at that. 11 kilograms. All right. So I do want to write this one out anyway. So we switch the screen over. So you for sure see this one. So you guys remember how I've been calling weight? There's a certain way I've been labeling it on the free body diagrams. I've just been calling it mg. Isn't that true? Right. Weight is mg, which is two variables multiplied together. It's mass times the gravity field. Right. Now, really, this works opposite of the way I wrote it. There is some gravity force, which is the weight. If you divide by the mass of the object, weight divided by mass, that's equal to g, which is the free fall gravity, which it's the same ratio for all objects of the planet. Okay. Now let's pop in those numbers. So actually, I'll do this backwards of how you guys solved it. If the sheep has a mass of 11 kilograms and it's on Earth, gravity field of about 10 meters per second squared, that would give it a weight of 110 newtons. Right? Okay. And then the way the question was pitched to you guys, and the Kahoot was, well, if the weight's 110 newtons, then what's the mass? So you just do 110 divided by 10, and you get 11 kilograms. Okay, you guys can switch back and forth between mass and weight. Right, in the metric system, it's real easy because just by sheer luck, free fall gravity is really close to 10 meters per second squared. Right, so you go from mass to weight, you multiply by 10. To go from weight to mass, you just divide by 10. And the corresponding units. All right, back up here. Uh, 15 newtons and 45 newtons act on an object in opposite directions. What's the net force? Yeah, 30 newtons. Okay, so opposite directions is key. So in that case, you subtract the magnitudes, right? 45 minus 15. Let me draw that up for you guys so you guys can see the free body diagram version of this. Okay. So suppose you got an object here, right? And maybe this thing has a weight of what was it? 45 newtons, I think it was. Okay. But 45 newtons that way. Okay. And it maybe this thing's like kind of in free fall, but it's also built up some air drag. And say the air drag builds up to like 15 newtons. Right? Is that so do you guys see that those two are going to subtract from each other? Another way to think of that is you could add these tip to tail. So you could take the tail of this guy, I like to the tip of this guy, and the resultant would be here to here, right? Which would be like 30 newtons. So 45 minus 15 is 30. 30 Newton net force. F net is 30 newtons. Okay. Yeah, there you go. Nikki, Luca on fire, Leah moving up, Alex, Olivia, top spot. This one takes some thinking. You would have the largest mass of gold if your chunk of gold weighed 1 Newton where? All right, a couple of you guys got that, the moon. Okay, so this one takes some thinking, like I said. So we switch over and show you guys why the answer is the moon. Okay. Here's one way to think of it anyway, right? So I got the moon, the earth, and Jupiter. Okay. So a little bathroom scale on each one of these surfaces. Okay. And then think, well, how much gold would I have to put on each one of these scales? Guess these are like digital scales, right? How much gold would I have to put on each one of these scales so that it weighs 1 Newton? Maybe I'll start with Earth. That's like the Goldilocks example, right? Maybe I need like this much gold. Let's do a little bag of gold. That looks fun, right? A little bag of gold going on right here. I need that much gold to get 1 Newton of gold. Okay. Okay. Now let's switch over to Jupiter. Guys, Jupiter, to also register 1 Newton of gravity force. You guys know Jupiter has a huge gravity field, right? So do you need a lot of gold or a little bit of gold to register 1 Newton? I'm thinking just a little bit. Here's your gold bag on Jupiter to also register 1 Newton. Hardly anything. Right? It's a huge gravity field. Now let's go to the moon. Right? Very weak gravity field. There's some gravity that's really weak. So to register 1 Newton, do you think you need like a big old bag of gold? Yeah, that's what I'm thinking too. Okay. So and that would be the actual largest quantity of gold, wouldn't it? Right? So each of those scales is reading 1 Newton. Okay. All right, we got Leia on fire taking top spot. All right. Equilibrium occurs when Oh, yeah, those are all true statements. Actually, we really only talked about two of these in class. So the net force on each object is zero. So that's true. We talked about that. Okay. You could get more granular and say in each direction it has to be zero. So we broke vectors into components, introduced a Cartesian system, and then broke them into components and said in the x direction and y direction has a zero up. Okay. Now this yellow condition we'll actually get to later in the year. You get to rotational stuff. That's also true. Yeah, all the statements are true for equilibrium. And right now you guys care mostly about the red and blue statements. All right. Got Leia on fire, still top spot. Alex, Luca, Olivia, and Nikki round out top 5. So this green guy's going to weigh 500 newtons. What is the tension in each strand of rope? It weighs 500 newtons. Notice he's hanging around right at the middle, right? Right the middle of that bar. Yeah, be 250 each, right? Which you guys kind of saw with the spring scales lab. You guys remember spring scales lab? You had like that vertical chain, and then one of those you like slipped an extra one in the middle, and the force divvied up. Yeah, kind of like that. So 250 up, 250 up, 500 down, they balance out. Okay. Now, if I add a little bit onto that scenario, because you guys did see him hanging right from the middle of the bar. Okay. What if put an extra twist on this? What if these? Okay. Let's get 2 bars going on. We got strands of rope pulling up like this. Okay. Now, if he was hanging right at the middle, then his weight splits half and half. So if he's like 500 newtons weight, you guys know that up here it's going to be 250 newtons, and here it's going to be also 250 newtons. I think that's a little longer right here. Right? So 250 up, 250 up, 500 down, they balance out. The way of saying that is that the sum of the forces is equal to 0 newtons, or the sum of the forces in the y direction is 0 newtons. Okay. What if though he's not hanging right at the middle? What if he's like 3/4 over to the side? What if he's hanging like right here? It's right there. Okay. Do you think that these tensions are each going to be exactly 250 newtons anymore? Probably not, right? Which one do you think has more tension? The one on the right or the one on the left? Which rope? How many of you guys think that one on the right is going to have more tension than the one on the left? Okay. Do you think these 2 ropes still add up to 500 newtons of tension though? Right? Okay. Now it turns out, I shouldn't have picked 500 times 3/4. Okay, here, I'll go ahead and give you guys the answer right now, and then we'll see how to get this a few months from now. This ends up being 375 newtons and 125 newtons. So it's going to come up to 125 newtons. Okay. But to prove that you don't just need the sum of the forces equal to 0, you also need to bring in torque. So we'll talk about that later. Just thinking ahead a few months now. All right. Friction is a force that always acts. How? Well, I don't know why I give you guys so much time on this one. All right, I'm gonna stop this in a few seconds here. Yeah, opposite of the motion. Right, so friction always wants to slow things down. Friction, drag force, it's going to be opposite of the motion. There you go. And we talked about that at the beginning of class today too. There you go. We got Alex on fire. Leia still holding on to the lead. What is the maximum resultant possible adding 3 newtons to 4 newtons? Yeah, there you go, 7 newtons. Okay. You want to draw this for you guys real fast, because some of those options are possibilities, just not the maximum, right? So how could you add 3 newtons to 4 newtons? Well, the answer was you could just add them tip to tail in the same direction, right? 3 newtons, 4 newtons, and then you get the resultants. Here, switch hue color for the resultants. Tail, or sorry, tip to this tail to this tip of 7 newtons. Here's that resultant. You also could have done something like this. Got 4 newtons this way, and then add tip to tail going backwards, so they oppose each other, 3 newtons. And that would give you a resultant of only 1 newton. That's like the minimum portion you get. So there's your maximum. There's your minimum. You see maximum, minimum. Okay. But you know what else we could have done that would have aligned with one of those possible answers? You could actually align these in any orientation, okay, including at right angles. Right? That's just one way. And then the resultant would be from this tail to this tip. Here's this resultant of 5 newtons. Get the 3, 4, 5 right triangle from Pythagorean theorem. All right. Okay. So there's different things you can do with those vectors, different ways to add vectors together. I got Luca on fire, Leia in second, Alex in first. What is the tension in the clothesline? Ooh. All right, so this one's a little tricky, but I'll take you guys. I'll show you guys why it has to be more than half the weight of the tire. And actually, it's related to something you guys did with the spring scales. Okay, do you guys remember this one right here? Okay, taking these spring scales into like 2 dimensions. Okay. So if you start out with them just like straight vertical like this, you guys remember each top spring scale, and they were 2. Okay. So each of them hold like half the total weight. Okay. So if you start from that point of view, there you go. Suppose you got a tire. I'll just replace that weight with a tire, right? Get ourselves a tire. Okay. Let's say the tire has a weight of like 500 newtons. Okay. Well, if the clothesline was like pretty well vertical, like pulled up like this, then you got 250 newtons here and 250 newtons here, just like your guys' lab. Okay. But then once you start to spread out that clothesline and make like a Y shape, anything beyond that, each tension is going to go above 250 newtons. So if I keep 500 newtons down here, if I do exactly 120 degrees apart from each other, I know exactly what number it's going to go up to. These are each going to go to 500 newtons. Okay, and then if it spreads out beyond that, they'll just even get bigger, bigger, bigger. Okay. Okay. So if they're straight vertical each, then they're each exactly half the weight of the tire. And if you spread them out, then they'll just increase beyond that. So more than half the weight of the tire. There you go. All right, Leia, back to number 1. Which has more mass, a kilogram of feathers or a kilogram of iron? Yeah, same mass, same mass, same mass, same inertia. If you put the same force on them, they'll both accelerate the same. Okay. Now they have different densities and different volumes, but same mass, same inertia. There you go. 1 kilogram is 1 kilogram. How much does a 5 kilogram bag of bolts weigh? Yeah, 50 newtons. You guys remember we did this with the sheep already, right? Going from mass to weight. All right, here, let's flip over. Let's do that. So, oops, let me flip my screen for the video too. There we go. You guys remember 11 kilogram sheep weighs 110 newtons? Well, how about a 5 kilogram bag of bolts? Put it in Earth's gravity field, it's going to weigh about 50 newtons, right? Just like that. So, really similar question to what you saw before. For mass to weight, again, in metric system, just multiply or divide by 10 meters per second squared. All right, Leah is on fire. Number 1, going into last question. 15 Newton force, 20 Newton force act in the same direction. What's the net force? Yeah, 35 newtons. So if you're pushing the same way, you just add the magnitudes. 15 plus 20 is 35. There you go. To the winner's podium. With the bronze, Luca. With the silver, Alex. And the gold, Leia. Yeah, confetti dance. Runners up, Harry and Nikki. All right, nice job, guys. Nice job. So got a couple minutes left here. Let's look at do a little Paul Hewitt right here.
So what's the force keeping it
Oh,
going?
wait, I don't do that one. Here, let's do this one.
Here's a ball. Hold it up here. And the ball is hanging. Now what I'm gonna do is I'm gonna pull this string, bam, 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 harder, 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 until either this string or the string's gonna break. Which one do you think will break? I'm pulling that down. Don't I exert tension in the string? Doesn't the string get tight? Huh? Twang, huh? Doesn't this one get tight too? And so I have a tension here. I also have a tension here. The string is stretched out. So as I pull gradually, which one's going to break, gang? Top or bottom? I'm going to say the top because I got another string here for the next trial. Let's watch this. It was the top. Because of the weight of the ball or because of the inertia of the ball? Check your neighbor and see if your neighbor sees which of the two properties, weight or inertia, made the top string break. Go. Why did the top string break? Because the weight of the ball is acting up here too. So the weight of the ball pulls on the top. The weight doesn't act on the bottom string. So I've got the weight of the ball pulling on the top string and the tension with which I pull on the top string. Both these, quick, boom, it breaks. But how about now I take this string and I whip it down quickly like that. Why did the bottom string break? Because of the inertia of the ball or because of the weight of the ball? Check your neighbor. I can show you that with this elastic game. This elastic. If I pull, I can pull. Look how much that thing's stretching. Okay, but let's suppose I just go like this. Notice that there was not as much force up here. The elastic that stretches when I pull quickly. That force was not transmitted up here. The inertia of that ball, it wants to sit right there, and I pull, it stays right there. Another word for inertia is lazy. The ball is lazy. It tends to stay doing what it's doing. See that? Now, what you get on the other side, slam that thing. Please don't miss the anvil. Do you have any grudges against your teachers?
All right, you guys have a great rest of your day.